Let's talk about radicals here. It's a quick little radical review. So to start, we have this sort of checkbox is our radical symbol. The number inside this wedge is known as the index of a radical. And then inside the radical, it's known as the radicand. Just have some terminology there. Now, something that we tend to forget, just because maybe as teachers we don't emphasize it and repeat it enough, but it's that there is one radical that we tend to use the name of this radical is for everything. And it probably also has to do with the fact that this radical, you don't write an index. But the index that's in here, that's never written down, we just assume it's there, is a 2. So another way to imply 2 is square. Usually a square is like an exponent, and that's because radicals are actually exponents that can be rewritten in this radical form. For example, if I make a quick note, you can write a radical as a fractional exponent or rational exponent. This just means you have a fraction in your exponent. And the numerator of that fraction usually becomes a power of a radicand, and the denominator is that index. But we write it this way. So we have a square root to imply the radical. But this is just this particular radical. There are more types of radicals. For example, there's the cube root. And this is the first radical you actually start writing the index. And that is the cube root. And those are the only two that have like special names, because after that you would just say 4th root, 5th root, 6th root, 7th root, 8th root, so on and so forth. They don't have any special name, hence they're sad about it. But you make sure you write the appropriate index in that wedge of the radical symbol. And just for a side note, you can write these as rational exponents. So you can write this, since they all have, you can say like a power of 1 here. Remember I said the power of the radicand is like the numerator of the rational exponent, and then the index is the denominator. So just something to keep in mind. You can always rewrite them as rational exponent. It's good to remember. But when you don't write the number inside that wedge, you are talking about a very specific radical, and that is the square root. It's probably the one that gets used the most. That's probably why the one we remember. But just know there are other radicals that do exist. And another rule, another note to make, just because we are going to be applying some of these operations, there's a neat rule, and this rule really comes from the rules of exponents, because like I said, a radical is an exponent, is that if you multiply two radicals together that have the same index, not the same radicand, but the same index, you can combine them into one single radical. And this equal implies you can go in either direction. So either combine them or separate them. So either way. This is going to become useful when we start doing some of these examples of these larger radicals. You might remember from previous courses that the square root of 9 is 3. But that has to do because of the index. The index is looking for that number of factors that can multiply to your radicand. So in other words, I'm looking for two numbers, since the index is 2, that can multiply to 9, but they need to be exactly the same. If you remember this factor tree, 3 times 3 gives you 9, and that is two numbers, hence the index is 2, that multiply to 9. 8, you're looking for three numbers that can multiply to this. So this factor tree is really neat. It can help you break a number down, which if you notice, you have 1, 2, 3. And because you found those three, your answer is 2. And of course, some of these smaller ones you probably remember off the top of your head, but this factor becomes really useful when you start dealing with really large numbers. Right? Like maybe we don't know the two numbers that multiply 256, right? But we can use our factor tree to start breaking it down, right? So 2 and 128. You can do 2 and 64. 2 and 32. 2 and 16. 2 and 8. And then we're going to keep going a little bit further this way, just so we have room. Or you don't always have to do 2, just to kind of go in both directions. We can do 8 times 8. This is 2 times, or you could do 4 times 2, and then 2 times 2. Same thing here, 2 times 4, 2 times 2. And why am I doing this? Because this used to help write the prime factorization of a number. That just means all the prime numbers that you can use to multiply and make this number. So for example, there's 1, 2, 3, 4, 5, 6, 7, 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. Let me move this one a little bit further down. Let me just show them. 1, 2, 3, 4, 5, 6, 7, 8. And remember, my index is 2. So I'm looking for two numbers that can multiply to 16. But I can also break this down into pairs. And every pair I can find, because the index is 2, any group of 2 or group of 3, I can use to simplify out of this radical. So let me just highlight here our pair of 2's. Here's another pair of 2's, another pair of 2's, and another pair of 2's. So that means I can make 1, 2, 3, 4 groups of 2. And the way I like to say is for every group, one of those numbers is going to come out. And as they were multiplying in the radicand, they're going to multiply outside. So 2 times 2 is 4, times 2 is 8, times 2 is 16, and bingo. So the square root of 256 is 16, meaning the two numbers that multiply to 256 is 16 times 16, which simplifies. And is this, if you knew it was 16, then skip it. You don't have to do this factor tree all the time. But it does become useful when the two numbers that you're trying to multiply does not exist. And what do I mean by that? I'll get to a number where this would be where we can apply this idea. But for now, let's just keep practicing. And one thing to note is we know that 2 times 2 times 2 times 2 gives us this 8, right? Because we did the cube root of 8. But all these numbers need to be exactly the same. So don't think, oh, well, negative 2 times 2 times 2 gives us 8. They all would need to be negative for this to work. And luckily it is. Negative 2 times negative 2 is positive 4, but times another negative 2 gives us negative 8. So that means our answer here is negative 2. So like I said, we made a group of 3's, and for every group, you're allowed to take out 1. Luckily, I have that. Now, some of these you should get to a point where you can do fairly quickly. Like you should know the square root of 49 is 7. The cube root of 27 is 3. The square root of 4 is 2. The square root of 25 is 5. Some of these you should kind of just, like snap of a finger, know what they are, right? Some, they need a little bit more practice, a little more work, but that's okay. Now, other ones that you need to be mindful of is, well, I said, I know 4. I'm looking for 2 numbers that multiply to 4. I know that's 2 and 2. But remember what I said. These 2 numbers need to be exactly the same. So 2 times 2 doesn't give me negative 4. And sure, I can make one of them negative, but then that doesn't make them the same anymore. So if I make both of them negative, that doesn't give me a negative 4. So this does not work. I cannot take the square root of negative 4 and get a real number. So not a real number. Now, you might be asking, wait, isn't there this idea of an I or complex number? And there is. So, by coincidence, I have I right here, this number. But yes, there is idea that the square root of negative 1 is I, which we'll talk about a little bit later. But for now, we're just dealing with real numbers, meaning if you look at the Arabic number system, we're talking about natural numbers, integers, whole numbers, rational numbers, irrational numbers, and that's a set of real numbers. Outside of that, there's a set of complex numbers. But we're just dealing with real numbers right now. Something to note, when the next topic we look at this idea of domain and range. We kind of had a slight intro before, but we're going to look at it more deeper in the next video. Now, cube root of negative 1 is negative 1. Why is that? Because negative 1 times negative 1 is positive 1, but times negative 1 is negative 1. Now, if you notice, that means for cube roots, and honestly it works out with any odd root, you can do negative radicants. With even roots, you cannot do negative radicants. There's no way of multiplying 2 numbers to give you an even number of times that will give you some negative number. And square root of 0 is 0. Why? Because 0 times 0 is 0. Even the cube root of 0 is 0. The fourth root of 0 is 0. It's just arbitrary. Because you can keep multiplying as many zeros as you want and it'll work. Same thing with 1. Right, square root of 1, cube root of 1, fourth root of 1, fifth root of 1. And now we get to the square root of 28. So this was the example I was alluding to with this larger radical. Here it's simplified nicely. And I did say that you don't always have to use this tree, but it is very useful when it comes down to a number like square root of 28. There's nothing wrong with the square root of 28. It's an irrational number, but it's still a real number nonetheless. But if we break this down, so we do 2 times 14, and then we do 7 times 2, and that's it. I can't break that down any further. So that means the factorization, the prime factorization, is 2 times 2, that was weird. 2 times 2 times 7. The square root, remember, is looking for 2 numbers that are the same or groups of 2 numbers. I have one group here, but I don't have a second 7 that would allow it to simplify outside of this radical. That group of 2's could simplify outside of the radical, but that 2 remains inside, which allows us to write this in a more, I don't know if it's simpler form, but a different version of this number. The numbers, we can write them smaller. Why am I allowed to kind of separate these? Well, I bring you back to this rule. Remember I said you can either combine them or separate them at any product. Now I'm choosing to create that separation right here. And this part is like saying square root of 4 times, and then this part is saying square root of 7, which that lets me simplify the 4 to a 2, which I did, and then just write it multiplying by 7. Luckily, writing them side by side in between here, this part implies multiplication, but we don't write it. So when there doesn't exist a perfect number that can multiply, two numbers that can multiply to a specific radicand, you can always just simplify the prime factorization and find the pairs or groups that you need based off the index, and any that don't have that additional factor needed to simplify, it can still remain inside of the radical, because you're allowed to split it at any multiplication. And the prime factorization is used to separate the number into different factors. So just in case you hadn't worked with radicals in a while, this is useful. Another idea for radicals that's really important, a little obsolete at this point, but still applied, and when you start dealing with calculus or in trig, is being able to rationalize either a numerator or denominator. The rules apply the same. All it is that because to rationalize it means it's going from being irrational to rational. So square root of 2 is an irrational number, and I want to rationalize the denominator here. So that doesn't mean I'm eliminating all the radicals. I'm just eliminating from the denominator. Now, the denominator would need an additional 2 for this to simplify. Well, this is where I bring back the rule that says if I multiply, I'm going to write it again. If I multiply two radicands with the same index, I can combine them into one. So, and remember the example we did on the previous video that I can alter a fraction visibly, but not its value, by multiplying by 1. So I'm just going to multiply by a square root to both numerator and denominator. And I said I would need one more additional 2. So I'm just going to add an additional 2, because once I combine them into one radical, that tells me I'm going to have square root of 2 over square root of 2 times 2. Because I can combine them into one. And that here is the square root has an index of 2. I'm looking for groups of 2. Not the number 2, just 2 factors. So that will simplify to square root of 2 over 2. And like I said, we're not eliminating the radicals. I'm just replacing it out of the denominator. But was able to move it back to the numerator. And multiplying by 1 allows the expression to still be the same. The value didn't change, just the visual appearance of it. And I can keep doing this, right? For example, here I want to rationalize the denominator again. But if you notice, this is a cube root. So I'm going to do cube root to both of these. But I'm looking for 3 numbers, right? 3 factors, because it's a cube root of 3. Sorry, it's a cube root. So the index is 3 is what I meant. So I only have 1 7, and I try to break it down. Like, are there other factors in this 7? And no, 7 is already prime. So I'm just going to bring in 2 more. But I need to do this to both numerator and denominator, because this is essentially saying I'm multiplying by 1. Now this is going to simplify to 2 times the cube root of 49 over the cube root of, and you don't have to write this every single time, the cube root of 7 times 7 times 7, because it combines all into 1. And that's going to simplify nicely into 2 cube root of 49 over 7. And just rationalizing the denominator. And then we have these examples. So these bring up the idea, something known as the conjugate. conjugate. And it's useful for an example that we're going to do right now. One of the difference quotients that I didn't get to. This is a conjugate. A minus B and A plus B are conjugates of each other. So I'm going to use the conjugate of this denominator, square root of 2 minus square root of 3. But once again, it has to be multiplying by 1. So I'm going to do the exact same thing to the numerator. This 2 is going to distribute. That's going to be 2 square root of 2 minus 2 square root of 3. And then I have to multiply the first to the second and the second to, the first to both, the second to both. Now it's going to say square root of 2 times square root of 2. Then it's going to be a minus square root of 2 times square root of 3. This is going to get a little long right now. I'm going to put this here. And then plus square root of 3. So that's going to be, now I'm doing the square root of 3 multiplying to both. I did square root of 2 multiplying to both. That's going to give me times square root of 2. And then minus square root of 3 times square root of 3. Now these two are going to simplify because, once again, there's that rule. If you multiply two radicals with the same index, you can combine them into one. Once this becomes 1, it's just square root of 2 times 2, which we know simplifies to just 2. Same thing with this, it's going to be a square root of 3 times 3. Well, that's the index is 2. I have a group of 2, and that's going to simplify to 1 of them can come out. And these two, I'm going to highlight. Remember, A times B is the same thing as B times A. So these two terms are exactly the same. One's negative and the other one's positive. So they are going to cancel each other out. And that will leave me with 2 square root of 2 minus 2 square root of 3 all over 2 minus 3, which is just going to be 2 square root of 2 minus, and then this just simplifies to 1. So my final answer will just be 2 square root of 2 minus 2 square root of 3. And the denominator was rationalized because it's just 1. And this is a neat technique to help you when you have two terms that are radicals. You can use the conjugate to help you simplify. And why did I do this? Well, an example we skipped was looking at this radical that we're supposed to do the difference quotient on. So the difference quotient, I'm going to do it all in one, is r of x plus h minus r of x over h. Now, finding r of x plus h is pretty quick because you're just going to plug in x plus h into that radical. And it's going to look like this. Square root. And I'm plugging x plus h, and there's nothing else I can do with that. Minus, and then I'm just going to plug in what r of x is, which is square root of x. Just so you can see, I'm just going to hit copy. I'm going to paste it, and this just goes right inside of here. I divide by h. Now, the question is, what do we do from here? There's no obvious idea of how to simplify this further, but we just talked about when you have two terms, what you can do. Now, again, the goal of these difference quotients is try to simplify this h. Well, there's an h in here. We can try to get that h out of that. And we're going to do that by multiplying by the conjugate. So it's going to be the square root of x plus h. Remember, this is a minus b, so the conjugate is going to be a plus b. And now we're essentially rationalizing the numerator. The last three examples we did was rationalizing the denominator. And let's see what happens. So I'm going to distribute. So that distribution is going to be square root of x plus h times square root of x plus h. And then, so that's the first multiplication. Now multiply to the next one, which is going to be plus square root of x times square root of x plus h. Now it's going to be my second term, and this is going to multiply to both. So that's going to be negative square root of x times square root of x plus h times square root of x times square root of x. And the denominator is just h times square root of x plus h plus square root of x. I haven't distributed anything just because I might, again, the goal is to simplify this h. And I can only simplify when things are multiplying, not when it's added in two terms. So I want to have it separate, all by itself, multiplying. And luckily, once again, see, this appears all the time. This is A, this is B, this is A and B. They're exactly the same, right? Hence, they are going to cancel. And these, at first glance, well, how do I simplify them? Well, again, the rule comes again. They both have the same index. They're the exact same radicand. So when you put them together, and you don't need to do this all the time, but this is just for the sake of this example. X plus h times x plus h. Well, remember, we're looking for two factors. I know they're weird factors, but that's still two factors. And for every group of two, you're allowed to take out one of those factors. Same thing with this square root of x times x. Those are two factors. I make a group of two, and for every group, I'm allowed to take out one of those factors. The denominator is still h times square root of x plus h plus square root of x. And that's equal to x plus h minus x all over h times square root of x plus h plus square root of x. Luckily, these x's cancel, leaving you with h over, once again, h times square root of x plus h plus square root of x. And if you notice, I can finally simplify this h. But just like I said before, just because you simplified it, that doesn't mean the numerator doesn't exist anymore. You always have that factor of 1, and that's going to be all over the square root of x plus h plus square root of x. You could just as easily have written square root of x plus square root of x plus h. Just like there's a commutative property of multiplication, there's a commutative property of addition. A plus b is the same thing as b plus a. As long as you keep the sign of the number, right? Because 2 minus 3 is not the same thing as 3 minus 2. But 2 minus 3 is the same thing as negative 3 plus 2. So the sign of the negative number stays with that number, and the positive sign stays with the positive sign. So something to keep in mind, and that is my difference quotient of the square root of x, right? So something to keep practicing. And the reason why we bring up radicals, and if you notice, it's in function notation, and that is because the square root of x defines a function. And what does it look like? Well, we just practice on evaluating a bunch of square roots. Remember, it's an even root, so no negatives are applied. but you were allowed to use 0. Don't forget 1 works, 2 works, but that was an irrational number, right? The goal was to simplify these into, right? If I'm gonna do r of 2, that's gonna be the square root of 2, which it is a real number. To be like, to give an approximate value, it's 1.4. But the idea is you want to have nice numbers to make it nicer to graph. The square root of 0 is 0, right? R of 1 is equal to the square root of 1, which is 1. And another number after 2, square root of 3, also simplifies to be like 1.7, 1.8. The next number that you might want to use is 4. Because the square root of 4 we know is 2. We don't know 5. It's still a real number. But I want to be able to graph this, so the next number I know is 9. And the square root of 9 I know is 3. Again, there's nothing wrong with 10 or 11, 12, 13, 14, 15. Those are all real numbers, but I would have to give an approximation or use a calculator. The very next number I know how to do is the square root of 16, which we know is 4. And of course, you can keep going, but this is enough ordered pairs to show me that we start here at the origin. We have 1, 1, and then we have 4 and 2. And this kind of just showing what a square root looks like. And again, the next number would just be 9 and 3, which would just move further down, which you can see kind of the path that this is taking. It sort of looks like this hill. And again, how do we check if something is a function? It needs to pass the vertical line test, and this definitely passes the vertical line test. And now looking at the cube root of x, remember this one, you could use negative numbers. So for example, we did the cube root of negative 8. That gave us, right, if we do f of negative 8, that will be the cube root of negative 8 is negative 2, right? Negative 7 is fine, negative 6, negative 5, 4, 3, all those. But I don't know the nice whole number of that. I do know what the cube root of negative 1 is that we did. It's negative 1. I do know the cube root of 0, which is 0. Same thing, I know the cube root of 1. I know the cube root of 8 is 2. Again, cube root of 9 is a perfectly good real number. So is cube root of 10 and 11, 12, 13, 14. Those are all perfectly good real numbers. But I don't know the whole value of it. It would be an irrational number. The same thing with square root of 2. The next number that we would know is 27, because the cube root of 27 is 3. That we would know by hand without needing a calculator. If you had your calculator, then negative 7, 6, 5, 4, 3, 2, 1, all those numbers are perfectly great. But let's see what this graph looks like. So 2, 4. So imagine this is negative 1, 2, 3, 4, 5, 6, 7, 8. And our y value is negative 2. So it's down here. So if you notice, I made the scale a little different. Hopefully I don't confuse anybody. But here I went by ones, which is like all these tally marks. And here I went by ones as well. It's just much, not a whole lot, but a little more spaced out, right? Just so you can see the graph a little bit nicer. So I'm essentially stretching it a little bit. Now, we have negative 1 and 1, which would be here. And then we have 0, 0, 1, 1. And then we have 8 and 2. So if you look here, the graph starts doing this. Just have to fix the shape a little bit. There, and then I have another one here following that similar shape, and this is what cube root of 3 looks like. So it kind of looks like a very stretched out S. And then square root of x has this hill. And since these are, and once again, does this pass the vertical line test? Absolutely. Hence it's a function. And here are two new functions that we can use. The square root of x, square root of 2. We can use transformation on these, right? Using function notation instead of equation, right? I could do square root of x plus 2. That would just move this twice to the left. I can do negative square root of x. That would just reflect it. That would reflect it on the x-axis. If I use a negative inside, that would reflect it on the y-axis. And so on. Same thing with the cube root. If I put a negative outside, it reflects this part up and this part down. If I put minus 2 inside, it actually moves that. Remember, it's opposite. It moves it to the right by 2. We'll do some more examples. But this is a quick review on radicals, the radical function, and the difference quotient on a radical.